So now we did all that, let's jump into lecture material for today. First off, our first question. What are the 3 basic units that we're going to be using to measure in this class?
Length, weight,
So we're going to measure lengths, we're going to measure masses, and we're going to measure times. What are our basic units going to be that we use to measure those things?
kilograms, seconds, meters.
Yeah, so it's going to be kilograms, seconds, and meters. Those are going to be the 3 basic units that we see over and over again, and we're going to be seeing combinations of those units. Now, you're often going to see these units with prefixes to specify different portions of that unit, multiplying it or dividing it by factors of 10. So it's often the case that we'll prefix a unit with a nano. Nano means 1 billionth. So, for example, when you see nm, that means nanometer. That means 1 billionth of a meter, or 10 to the minus 9 meters. A nanometer. So nano is one of the prefixes you'll see over and over again. Another one you'll see a lot is micro. Micro is 1 millionth. So a micrometer is 1 millionth of a meter. The symbol that we use for micro is mu, that Greek letter. Why don't we use little m for micro? Because we use little m for milli.
What about big M?
We don't use big M's. We keep our units all lowercase all the time. So milli is 1/1000, a millimeter. And you'll see mm for millimeter. That one you likely came across just throughout the course of your life.
1,000.
Yeah, so milli is 1,000. Centa is 100. That's why a penny is called a cent. It's 100th of a dollar.
That's good to know.
So centa is 1/100th. Centimeter is 100th of a meter. And then the other common one is going to be kilo. Kilo means 1,000, and so a kilometer is 1,000 meters. And you'll also see this, a kilogram. For some reason we use kilograms rather than grams as our basic unit. Just what we come into contact with in our daily lives, but obviously a kilogram is 1,000 grams, as an example. Okay, so different unit prefixes you'll commonly see. I think that there's a table somewhere in your book, an appendix that has all the common ones we use. Any questions with that? Okay.
Is it crucial for us to memorize that?
Yeah. You're going to need to be comfortable with it. When you see nanometer, you cannot be thinking in your head, oh, okay, nano is what? You need to just get comfortable with these different sizes. There's a way that you're already instantly comfortable with a centimeter being 100th or a kilometer being 1,000.
Yeah, those. So we need to know it's like 1 billion.
Milli, micro, nano. Yeah, they come up a lot. It's going to be annoying having to look it up, but we'll see those units come up so much, you'll probably just get used to it just by being in the class. The same way like with logic, you always got used to me like using quantifiers or whatever.
No.
No.
You should.
You didn't do logic. I keep forgetting. Okay. Now, it is extremely difficult for us to try and get any intuition for just how big or how small these types of numbers are. When you see like something 10 to the negative 9 or something like 10 to the 9, it is very difficult for us to even have any intuition as to what that means. So we're going to do a little exercise here, a little applet for giving you different scales of things. So here's roughly 1 meter, here's a guy, here's a basketball. It's showing you the sizes of things roughly. And just for the heck of it, I want you to try and guess something that is roughly 10 to the 12 meters and something that's roughly 10 to the minus 12 meters.
10 to 12, okay.
10 to the 12 meters and 10 to the minus 12 meters.
Guessing 10 to 12.
10 to the 12, are we talking like radius of the Earth? Are we talking about like distance of the Earth to the Sun?
We're talking like solar system to solar system, I think.
Solar system to solar system. So like basically distance between stars, you think that that's roughly what that is?
Is that trillions?
What?
Is that trillions?
Trillion. Trillionth.
Okay, so it is.
Our numbers are named stupid. So 10 to the 3, for some reason we call 1,000 instead of million. So when it has one group of zeros, we call it 1,000 instead of million. When it has 2 groups of zeros, we call it million. When it has 3 groups of zeros, we call it billion. But the bi in billion means 2. When it has 4 groups of zeros, we call it trillion, but tri means 3. And so for historical reasons, our numbers got named the way that they're named, and so, yes. It's always 3 off from what you want it to be.
Okay, so that's trillion.
So this is trillion, this is trillionth. So we're roughly thinking distance between stars on this one.
A trillion
There's
meters.
no picture. Are you saying from the image?
No, ignore the image for a second. We're going to do the image, but
Oh.
I just want you to just try and guess. What's roughly a trillion meters?
A trillion meters really well. Actually, that's
That's
a lot.
way bigger than our universe. Or bigger than our galaxy.
Bigger than our galaxy.
That's, I don't know if I go that far.
So you're talking like distances between galaxies is what you think this is?
Milky Way, yeah.
The
How much is it?
our galaxy is the Milky Way. Did you mean solar system?
It's for
What's,
sure
our,
bigger
what's
than
the difference between us and the sun?
It's a few million meters.
Us and the sun is 93 million miles, if I remember.
Yeah. So that's a lot of meters.
Oh, so yeah, just solar
92
system.
million miles.
Right, the solar system.
So you think this is roughly
No, it's gotta be way bigger.
Galaxy.
It's gotta be way bigger.
size of the solar system?
Galaxy.
This size of a galaxy?
That's a big jump though.
That's a
How
big
many
jump.
Galaxy, how many solar systems do we have?
Billions.
Oh, so we definitely got that.
There's billions of solar systems in the galaxy.
A couple of solar systems.
So distance between stars roughly is what he's kind of settling on. 2 stars in a solar system.
That's somewhat accurate, maybe.
We're going that big. I want you guys to kind of come to somewhat agreed upon consensus here.
A trillion is a big number.
A trillion is a big number, but that's also a really big number you're saying, or a big distance you're saying. So.
Well, it's not big on. It's not big on. Yeah. Yeah, I don't know. I can't.
Roughly distance between stars is what we're
I
saying.
think it's probably.
All right, roughly distance between stars. So we'll just put stars there to remind us. And what do we think this is?
Yes.
Just roughly.
That's gotta be like. Well, a nanometer is like a few atoms across, isn't it? Nanometer is.
We're gonna find out.
I think nanometer.
A nanometer is a few atoms across.
Well, think about it. Like, there's like a talking about computer chips, and their transistors are like 4 nanometers or something. They have tiny transistors that are like 100 atoms across.
How did they make those?
I don't know if I'm basing my intuition on that.
It's
So what are we thinking? Size of an atom here?
a neuron, proton.
Size of a neuron? A neuron is a cell. That's much bigger than an atom.
Much bigger than
What
that.
is it?
A neuron is like in your
Neutron?
head.
What's it?
A neutron.
Neutron.
A neutron is a component of an atom. It's a piece of an atom.
Yeah, neutron.
So we're thinking neutron
I don't know. Maybe.
or atom.
Atom, maybe. Atom. I don't know. I don't know.
All right, we need a tiebreaker here.
Neutrons are bigger than protons, right?
They're basically the same size.
Neutrons.
We're gonna go neutron. All right, so we got a neutron and we got stars.
Okay.
Now let's roughly do this.
It's a big spread.
It's a big spread. Yeah. So here we are at 1 meter. Let's span out, span out, span out. Here we are at roughly 1,000 meters. There's the Eiffel Tower, the Hoover Dam over there, the Great Pyramids. So that's 10 to the 3. Let's
Random all words.
get to 1,000,000 meters. There we go. We're 2/3 of the distance crossing California, almost the span of Italy at 1,000,000 meters.
Some planets.
There goes Earth, there goes some planets.
Minecraft world.
There we go, 1,000,000,000 meters. We're looking at some really large or some really small stars are roughly 1,000,000,000 meters across. There we see our sun. So there we are, 10 to the 9. Now we gotta get 10 to the 12.
This is from Earth to Sun right there. That's 10 to 12.
And so 10 to the 12, you're looking at, there's some stars in our universe, almost 10 to the 12 in terms of their size.
I'm way off. I'm way too far now.
So distance from the Earth to the sun is right there.
Way too far now.
It's
Or
1
211.
trillion. Well,
So here's 1,000,000,000,000 meters.
10 to the 12 is a lot smaller than the distance between stars.
Yeah.
Way smaller.
Yeah, we haven't even gotten to the size of the solar system yet.
big things. Those are
Wow, I
stars,
was
right?
way off.
Yeah, those are still just stars. So there's some stars as big as what you're talking about, not distance between stars.
I was way off.
Yeah, there's some massive stars. There we go. We got the Kepler belt, or Kuiper belt. That's basically looking at our solar system. 1 light day, how far light goes in a day. Light can roughly cross our solar system in 1 day. And here we go, getting to 10 to the 15
Now
meters.
Now we're at stars. Okay.
So
We're past stars, now we're getting to nebulas. Nebulas will collapse into stars.
No, we're distances to stars now.
Why don't you teach me astronomy class?
And then there we go, 1 light year. We're getting to some bigger nebulas. Your closest stars are going to be some number of light years away. I'm not sure how far away the closest one is, but a few light years.
So the Oort cloud is going to be, is that the objects in the mass of the sun?
I'm not sure what the Oort cloud
I
is.
think it is.
And then here we are, we're at our next one, 10 to the 18 meters. Now we're getting to the size of some of our bigger nebulas, probably getting some galaxies close to that size. I'm not sure how many of those are. Okay, there's our first dwarf galaxy right there. So now we're on the scale of galaxies at 10 to the 20, 10 to the 21. Here we come. And 10 to the 21 meters gives you the size of, here's a galaxy. Let's not, oh, our Milky Way galaxy is going to be up here, so it's going to be roughly on this scale.
Yeah,
So-
we were both way off. It was definitely a lot less than.
So you guys were all over the place.
I thought it was just between stars. It was way shorter than that. Way
And so gives you a sense for how stupid massive our solar system or our galaxy
This
is.
is the distance. This is distance.
Distance to the next galaxy is right there.
What is this in terms of meters? Like,
What is this in terms of meters?
What?
This is, we're at roughly 10 to the 22. 10 to 22.5.
how many zeros is that?
22 zeros.
22 zeros?
Yeah.
How long does it take light to go between galaxies? Is that possible?
Yes, it's possible for light to go between galaxies. That's how we can see other galaxies.
Hundreds.
So there's 10 to the
20.
24. Now we're looking at galaxy clusters.
Great wall.
And
Guys.
zooming out, there's the observable universe, roughly 10 to the 27 meters across.
Dang.
That's
So that's zooming out. Now let's go back down in.
holy. That's crazy.
Yeah, we're kind of small guys.
Yeah, we are extremely small. So now we're zooming in. We're on the centimeter scale here. Here's 1 millimeter. There's the thickness of paper, less than a millimeter thick. Zooming in, zooming in. Here we got a micrometer, about the size of some viruses. There goes DNA. We're at 1 nanometer now.
Oh, so I was a little off.
So nanometer, you got a buckyball, that's composed of carbon
Hey, see,
atoms
hey,
over there,
we were
glucose
close.
molecule.
We were close.
Yeah, that's when you guys are much closer on.
So not an atom or a proton.
It's
No,
not
you guys are
about-
going to be really close to right on the money on this one. So there goes a hydrogen atom and a helium atom. Those are going to be our smallest atoms. There goes a gamma ray, and here we are at 10 to the 12, or 10 to the minus 12. And we'll be coming up now on 10 to the minus 13, the nucleus of some atoms,
Yes.
with there being individual protons and neutrons. So
Oh, we're not
Off
even-
by a degree of one.
So there's proton or neutron, off by a factor of, those are 10 to the minus 15, so you're off by a factor of about 1,000.
That's not that bad.
For what we're doing, that's not
We
bad
were
at
off
all.
by a factor of like.
So there's 10 to the minus 15. Zoom in 1,000 more times. And there we got 10 to the minus 18, looking at different quarks. Zooming in 1,000 more times.
Are we coming up to string?
And there we got 10 to the minus 21, your top quark. Zoom in 1,000 more times.
What are these things made of?
I don't remember.
Those are our fundamental components, but supposedly made of different things. Now we don't know about anything in between. Nothing. We're zooming in 10 to the minus 30, minus 31, minus 32, minus 33, minus 34, and there is 1 Planck length.
And you
Just
can't
string
just water
theory.
that, right?
Distance no longer makes sense on scale smaller than that, according to current theory. The concept breaks down.
String theory.
So there we go. That gives you a sense for the scale of the universe. Goes from, what was our biggest one, 10 to the 27?
26, 27,
10 to the 26, all the way down to 10 to the minus 35. So there's more to go down than there is to go up
I bet
by
you-
many, many, many orders of magnitude.
But you get a lot of just emptiness when you get down to the bottom.
So far, who knows what our model will change to. We're well below what's observable. The nice thing about bigger objects is they're easier to see, in a manner of speaking. So that gives you a sense for the scale of the universe.
Fun.
Okay. And for different things at different sizes, because it is just almost impossible to come close to appreciating how big and how small some of these things are. We're just wildly guessing. And even when we're close, we're off by 1,000.
Yeah.
Right? Okay. So that's the apple I wanted to take you through. Give you a sense for the size of the universe. Next thing we want to talk about is consistent units. Okay, so when you're solving physics problems, you're going to have to do sanity checks. You need to ask yourself, does my answer even remotely make sense? And one of the great ways to do that is to check the units. So for example, you've used over and over again that distance is equal to rate times time, right? Now let's check that really quick. Give me some speed that we could travel at.
6 meters a second.
So we could go 6 meters per second. And now give me some number of seconds. 10 seconds. Keeping it nice and simple. When we do our multiplication here, the seconds cancel out with the seconds, and we're left with 6 times 10, which is 60 meters. It came out to a distance. And so, sanity check says we did it correctly. We got a distance out when it was all said and done. A lot of the problems that you're going to have is losing track of your units. And your units are going to come out not making any sense. Like if you would have been pedantic on the quiz that we just did, what were we converting, 10 meters or something like that?
10 meters cubed.
Yeah, 10 meters cubed. If you would have been pedantic and you would have multiplied it out and did converting it, we'll just convert it to centimeters really quick. How would you do that? It's 100 centimeters in 1 meter, and do it again. 100 centimeters in 1 meter. Do it again, 100 centimeters in 1 meter. If you want to convert the meters cubed. Doing what some of you did, if we would have just done it like that, notice what happens with our units. 10 times 100, we're going to get 1,000. But what are our units here? Meters cancel out with one of those meters, and we're left with meters squared centimeters, which are not the units that we're looking for. We were looking for cubic centimeters.
That helps a lot.
So it's called dimensional analysis, making sure your dimensions make sense. I often call it doing a sanity check. Is your answer even sane? Check it.
Right.
Okay.
Can I put light on, by the way?
Huh?
Can I put light on?
We'll be looking at stuff here in a second. I don't know, whatever helps you guys see it better. If this is hard for you to see, go ahead and flip it on. Okay. So next thing we need to talk about is significant figures. Now remember, how does the scientific process start? What's the first thing we do?
Ask you a question. Observation.
Don't give me the scientific method. Big boy from last week. What do? How do we start?
You observe and you find.
You observe facts and you inductively reason on those observable, quantifiable facts. Quantifiable fact meaning it's, in some sense, measurable. So it comes down to measurements. And let's say that me and Zach here are trying to measure the area of this perfectly rectangular room. Pretend it's rectangular. And I'm over here, and I've got a meter stick, and I'm trying to measure out this wall. Now, if I'm laying out my meter sticks, how precisely can I really measure this room?
Pretty precisely.
Maybe to within like a centimeter if I'm lucky.
Yeah.
So let's say I'm able to get it within a centimeter. And so I measure this out, and it comes out to 6.27 centimeters.
Meters?
Thank you, meters. Getting it to within a centimeter of accuracy. Now when I write that 7 there, I do not mean that it came out to exactly 7 centimeters. All present. Brooklyn is still on my rule for this class.
I'll fix it.
Okay.
I forgot scan in though.
Scan in.
So you do it in devotional, and then you scan in the afternoon.
Is that everyday thing, or is this a calibrating it?
Every single day.
Okay, that's good to know.
Thank you.
Okay, so we get it to within a centimeter of our measurement. But did it come out to exactly 7 centimeters?
No.
So when we write this unit, this is understood in how we're writing it. When we say 6.27 meters, we are saying that our answer lies somewhere between 6.265 to 6.275 meters.
4. Right?
We're saying that if you were to round it, it would come out to this number,
Yeah.
whatever it is.
Would that be 7.4 though? Because you're right.
Okay, let me write it exactly what it would be. Here's what we're saying when we write that number. We're saying that your number is in this range, 6.27 or 6.265, sorry, including that, to 6.275, not including that. Okay. It's in that range.
Okay, I see.
So that's precisely what it means when you write that number right there.
Right.
And so that tells you how carefully you did your measurement. It would be very, 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 very wrong of me to have put like a 3 here if I approximated and 3 millimeters, if I can't really measure that well. So you're communicating how well you're measuring. Let's say on the other hand, Zach is measuring it this way, and he's using some really precise measuring device. Something super spectacular at just getting it down to very well. And he measures it, and it comes out to exactly 4.276159 meters. So his measuring device is very precise, and it's able to get this much accuracy on it. Me, I'm just using my poor little meter stick. This is how well I'm able to measure it. Now, when we try to now approximate the area of the classroom, how do you get area if we know the length and the width? You multiply them together. So I come, I get my calculator, and I write 6.27 times 4.276159, and I get, yes, it's 26.8115 meters.
But you don't know that. for sure.
But we don't know that because we have no clue how accurate this number was after the 7. And so this is very misleading. If I were to write this, squared, if I were to write this as the area, my reader is justified in assuming I carefully measured all the way to this decimal place. When in reality, how should we have written it? Since we only knew mine to 3 significant figures, then when it's all said and done, our answer should only have 3 significant figures. So the correct way to write it would have been 26.8 meters squared.
What?
So this is where I got it wrong last time. Why wouldn't you go all the way to the 1?
Yeah, that's what I'm wondering. You had 2 decimal places before. Why would you have 2 decimal?
We have 3 significant figures here. It doesn't matter that they're decimal places.
I see.
Let me show you why it doesn't matter that they're decimal places. Suppose I told him my measurement was 627 centimeters. That doesn't change anything. It's still the exact same number.
Yeah.
It's known within 3 significant figures. So where the decimal point comes up in these measurements is completely irrelevant. What matters is to what degree you know it. So when you multiply 2 numbers together, you only use as many significant figures as the smallest number of significant figures you had in your product. So since this had less significant figures than this, we use however many significant figures this thing had. And so when we write our answer, we write it this way, not this way. Because we have no clue. If we were to do this measurement more carefully, and then redo our product, then this second digit probably wouldn't have been a 1. Could have easily been a 2 or a 3.
Yeah.
We don't know. So when you multiply, then you use whichever number has the least number of significant figures, you use that many significant figures. Now what about adding? So now let's imagine that I measure, me and Zach were trying to approximate the length of the entire school. So I measure 2 classrooms lengths, and I get something like 14.73 meters. Again, I can get to within a centimeter. He's got his crazy good approximating tool. He measures the second half of the school, and he comes out to 14.739264113. Well, I'll pretend that was more like a 2. We'll pretend that the school's nice and symmetric. And he comes up with this measurement for how big the second part of the school is. Now we want to guess the length of the entire school. So obviously we add the two numbers together, right? And so if I add those two numbers, if I do 14.73 plus 14.73226,413, and I get 29.46226413 meters. Why is this an incorrect way to write it?
Because it's still your significant figure.
Gray area after the
Yeah, what number should we have written here?
6. Just end at 6.
End at the 6. So he's correct, we should have ended at the 6 here. And the reason we end at the 6 is because this one's decimal places from there on out, we don't understand what they could have been. And so when you add, you now use the least number of decimal places. So this was kind of a bad example. Let me do one more really quick. So one more example like this. Say me and him were both going to measure something. I do the first measurement, and I get that it was 1.76 meters. He does the second measurement, and it comes out to that. Let's say 1.7 meters. Okay. So I measure the first little piece of something. He measures the second piece of it. What's the total length? When we write our total length, how many significant figures should we use?
2 significant.
You should have one decimal place.
We should have one decimal place.
2 significant.
So it's going to come out with 3 significant figures. 14, it's going to be 16.43226,413 meters. But we only knew this one to within a tenth of a meter.
Yeah, isn't everything after the decimal?
And so everything after a tenth of a meter over here we can't use because we don't know what those digits would have been over here. So here's what we should have written, 16.4 meters. So when you multiply, you use a number with the least number of significant figures. When you add, you use the least number of decimal places. Multiplying, least number of significant figures. Adding, least number of decimal places.
You mean add everything after the decimal?
Since this one only went to one decimal place, we can only use this number to one decimal place.
Yeah.
We can't continue adding these decimals to these decimals because we don't know what they were.
Yes, but you count it after, so your decimal, then you start counting how many you use.
Here's how many. Here's the correct answer.
Yeah.
This one only had one decimal place. This one had several decimal places.
Yeah.
We only use one decimal place. Okay. And it doesn't matter if I had another one right there. That would put a one right here.
Yeah, because it's everything after the decimal that you count.
We count the number of decimal places, the least number of decimal places. I don't know what you mean. This has one decimal place.
Yes,
he's saying
we're saying
okay.
the same thing. I think we're saying the same
Okay. So, good?
Makes sense.
So that's significant figures. Scientific notation. Do you guys know what scientific notation is?
Yeah.
Yes.
So when you get some number, 6.2, well, let's not do that. 6235.2971 meters, let's say it's that. And those are all our significant figures. When you express it in scientific notation, you do your first digit, decimal, then all the rest of your significant figures, whatever they are. And then you multiply it by whatever 10 you need to restore your number. So how many times do I need to shift my decimal place to get back to that number? I need to shift it 1, 2, 3 times. So times 10 to the 3 meters. So when you write in scientific notation, you're only going to have as many as your significant figures are. And you always only have one non-decimal place number. One digit before the decimal, all the other digits come after the decimal.
And you count after, so that wouldn't be 4. It would be 3.
I don't know what you mean, but sure.
Yes.
This goes to that.
Yeah.
After you shift the decimal place 3 times.
I think I got it.
Okay. So we got that. Let's now do some examples. So examples 1.1 through 1.4 in the book. So, example 1.1 says, The world land speed record is 763 miles per hour. So we got 763 miles per hour. There's our units. Set on whatever, Express this in meters per second. Meters per second. So we're trying to do that conversion. Miles per hour to meters per second. Good? Now, something I always just keep in the back of my mind is that meters per second is roughly half miles per hour. Because this is a common conversion. So just sanity check. I'm looking at this. 763 is close to 770. Half of 770 would be like 385. So I know I'm in the 385 ballpark. Somewhere around there. Good? So that's just quick sanity. Now I'm actually going to do the conversion. Huh?
Okay.
It's just something I keep in my mind. Is that meters per second is roughly half miles per hour. 40 miles per hour is roughly 20 meters per second. I keep that roughly in my head. It's more like 3/7. So actually I should expect 770 divided by 7 gives me 110 times 3. Really, I should be thinking more like 330 will be close to the answer. So that's really what I keep in my head, but I thought that might make the math harder, but it came out nice.
So 3 out of 7, 3 over 7.
Yeah. So should come out in that ballpark. Okay, so now let's do the actual calculation. So I have 763, and this is miles per 1 hour. And converting the units, I need to convert miles to meters. How am I going to do that? First I got to convert it to feet. To feet. So how many feet in a mile? 5,280 feet in 1 mile. Notice that 5,280 feet and 1 mile are one and the same thing. So I'm taking this number and I'm multiplying it by 1. When I multiply a number by 1, I don't change it. Still the same number, just different units.
Yeah, okay.
Okay, so that gets us to feet. Now we gotta get to inches. So there is 12 inches in 1 foot. Now I gotta get to centimeters. There is 2.54 centimeters in 1 inch. Now I gotta get to meters. 1 meter is exactly 100 centimeters. Okay? Now we have hours here. I need to get to seconds. So 1 hour, I'm not going to do minutes to seconds. I'm just going to go straight to seconds. It's easy enough. It's 3,600 seconds. Good? And then you throw it all on your calculator and some number should come out. If you mess something up, that's why it's nice to have this in your head, because it's easy to accidentally forget to divide by the seconds or the meters or whatever. So those are easy mistakes to make plugging into your calculator. So 763 times 5,280 times 12 times 2.54 divided by 100 and divided by 3,600. And the answer I got is 341.092. So 341 meters per second, 3 significant figures, because I had 3 significant figures on this. And so the answer the author gives 341.0 meters per second, and that's because he said that this was 763.0 miles per hour. So I messed up. He wrote it like that with 4 significant figures. So doing this all with 4 significant figures, a 0.0 comes out.
Do you always write out the conversions before you do it?
No, I will never write out these conversions again, and you'll just do it in my head as I plug it into the calculator. I'll just say out loud, multiply 5,280 gets me to feet, multiply by 12 gets me to inches, multiply by 2.54 gives me to centimeters, divided by 100 gets me to meters, divided by 3,600 gets me to seconds. So you'll know, and I'll tell you when I'm plugging it on my calculator typically. I won't write it out like this, but it's very safe to write it out like that. So good practice. Good to do if you have like extra time on test or whatever, to actually write it out, make sure you didn't mess something up. Okay, so our next example problem, example 1.2. The world's largest cut diamond is the first star of Africa, blah, 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 blah. Its volume is 1.84 cubic inches. So make sure we get the right significant figures this time. 1.84 inches cubed. We have 3 significant figures. Express it in cubic meters. Okay, so expressing it in cubic meters. I'll write it out stupid one more time and then I'll stop doing this. So 1.4 inches cubed times, we need to convert this to cubic meters. So inches first to centimeters, then to meters.
Oh, duh.
Okay, so 2.54 centimeters in 1 inch.
Do we have the conversions to meters to feet? So we could.
You can memorize those if you want. You can always memorize numbers to skip steps. These are just well-known conversions. So this gets me, and that will cancel out one of the inches. I got to do that 3 times to cancel out all 3 inches. 2.54 centimeters in 1 inch times 2.54 centimeters in 1 inch. Okay, so that got us to cubic centimeters. Now I need to get to cubic meters. So 1 meter is 100 centimeters. Times 1 meter is 100 centimeters. Times 1 meter is 100 centimeters. Okay. So, plug it into our calculator. We get 1.84 times 2.54 3 times, or 2.54 cubed, and then divided by 100 3 times, or divided by 100 cubed. And the answer we get is, just telling you exactly what my calculator screen here says. It says 3.015219776 times 10 to the minus 5 meters cubed. Now that's obviously not our answer. How many significant figures did we have? 3 significant figures. So doing 3 significant figures, rounding to 3 significant figures, gives us 3.02 times 10 to the minus 5 meters cubed. And the author writes for his answer 3.02 times 10 to the minus 5 meters cubed. Okay, exactly what we got. So got example 2 right. Okay. Example problem 1.3. Let's see what that says. The rest energy E of an object with mass m is given by Einstein's famous equation E equals mc squared. Find the energy for an electron with 3 significant figures, where the mass of the electron, try and just absorb this for a second. What's the mass of the electron? 9.11 times 10 to the negative 31 kilograms. Try and appreciate how stupid small of a number that is. It's a ridiculously small number, and what's nuts is we have that measured to 3 significant places. How on God's green earth are we able to measure something that ridiculously small? It's nuts. But apparently it's been done. And we know the speed of light measured very well. It's 2.9979245 times 10 to the 8 meters per second. Speed of light. You with me? Okay, so all we got to do is plug in mass of the electron times the speed of light squared. And so we take the mass of the electron, I have these values stored on my calculator because you use them a lot, times c squared is equal to, just telling you exactly what's on my calculator here, 8.18766 times 10 to the minus 14. Now we had 3 significant figures with the mass of an electron.
So that should be 8.1, right?
Let me double check. Mass of an electron was, 9.11. Okay, so it should be 8 point what?
8.19.
8.19, good. Times 10 to the minus 14. You don't know these units, but they're joules. Joules for energy. Oh, sometimes we do use capital letters, because you typically use capital J for joules. So I lied to you when I said units are always lowercase. That was a lie. Yeah, now I think about it, we use uppercase all the time.
All of my questions go back.
Okay, and let's see what he got. 8.19 times 10 to the minus 14 joules. Okay. We did it. Woohoo. Let's see how many. I was going to do 1.4 next before we move on to the next topic. So 1.4, you are writing an adventure novel in which a hero escapes across the border with $1 billion worth of gold in a suitcase. Could anyone carry that much gold? And would it fit in a suitcase? So we're going to have to do some rough approximations here. I don't want to look up what all these numbers are. So he says gold sells around for, you guys can go through this one yourself. It's going to have you approximate it, but it turns out the gold's not going to fit. So this is teaching you, this problem is supposed to be walking you through guesstimating. I'm actually going to skip over this one.
And he's certainly not going to be able to.
But he's definitely not going to be able to do it.
You're saying he didn't fit that much?
No, you cannot fit $1 billion worth of gold into a suitcase.
Yeah.
So they came up with an approximation, $1 billion worth of gold is going to weigh about 200,000 pounds. Now, from when the textbook was written to now, maybe gold has doubled in value, so it'll still be 100,000 pounds or 50 tons. So, still can't do it. And then they want you to redo it with diamonds. We're not going to go to that one, but not a bad problem. You guys already read through the problem, of course, right?
Yeah,
Of course.
Of course. So, we'll skip through that one and move on to the next topic, which is
Displacement.
getting to vectors.
Oh, heck.
So,
There's a dot.
They're terrible.
There are a little bit unintuitive, but not even really.
Yeah. Just be
just need to make sure we can fit whiteboard and camera. And let's see. You can see to about right here, right?
That line is not in it.
That line is not in it.
No. I don't know.
I just barely missed it though, okay. So this line is going to be in
Yeah, that line's.
it. Okay. So just give me a sense for the space I have. All right. So a vector. We're going to be doing tons of math with vectors in physics. We use vectors and scalars to model pretty much everything in our universe. A scalar is just a single real number for our purposes. That's what a scalar will be, a single real number. What is a vector going to be? This is a lie, but it's the lie you're going to believe. A vector is an ordered collection of real numbers. So a scalar is when it's just one real number. A vector is multiple real numbers in a collection, like a list.
That's how the book defined it.
The book is going to call it magnitude and direction.
With direction,
Yeah, that's what your book called it. Okay.
What's the actual definition?
Of a vector?
Is it like an object in a vector space? Or?
Yeah. What is a vector? It's a member of a vector space. It's something that satisfies the axioms of a vector space. Just like what's a real number? It's a member of the real numbers. It's something that satisfies the axioms on the real numbers. So it's kind of a bad question to define what a vector is. So the useful lie that we're going to believe is it's just an ordered collection of real numbers.
Which makes sense.
Or directional. Is directional a bad way to look at it?
It's a magnitude and a direction.
Is that a bad way to look at it?
So you're going to need multiple numbers to encode a magnitude and a direction.
Yeah, you want.
It's going to encode the same thing.
So okay.
We're going to use multiple numbers to encode a magnitude and a direction. So yeah, you can think about it that way if you want, that your author thinks about it that way. So I let the author say it that way, and I'm going to say it this way. Okay, so notation for a vector. We will use a letter, and then we will put this arrow above it to say this is behaving as a vector.
Or with the direction.
Sure, it has a direction. What direction does it point in? It points in the 2-7 direction, whatever that means. Or, in other words, it's just an ordered collection of numbers. The vector 2, 7. We use these angle brackets when we're saying we're going to treat this ordered collection as a vector. So, I'm going to be using these angle brackets all the time. I don't think the author even introduces this angle bracket notation until later.
That's not.
But, so angle bracket notation, here's the vector 2, 7. Here's another vector, the vector b. It's just some ordered collection of real numbers. Pi 1/2, 2.76. Just a vector. Good so far? Okay, we're going to define some operations on these vectors. So let A be the vector with the two real numbers A1 and A2. And this could be like 1.76, that could be negative 19.215, whatever.
Okay.
So A is just two real numbers. It's this vector. B is just two real numbers. C now is just some real number, like 17. So we're looking at vector, vector, and some real number. Now, just terminology, we call this a two-dimensional vector and we call this a two-dimensional vector because it's two real numbers. So we'll only be dealing in this class with two-dimensional vectors and three-dimensional vectors.
Is that what they mean when you have like a couple dimensions in mathematics? Is they
Yeah.
just keep adding?
Sure, that's exactly what it could be.
Okay.
Yes. This vector would exist in a three-dimensional vector space.
Are there one-dimensional
Oh,
vectors?
Sure, but you can also just treat them as scalars, so who cares? So for the purposes of our class, we won't talk about one-dimensional vectors except for accidentally, meaning the second place will be a 0. And so it's just going in one direction, one dimension.
Is that like a unit vector?
Yeah, you can, kind of.
Kind of.
We won't talk about one-dimensional vectors. Okay, there's two-dimensional vectors, three-dimensional vectors. Let's not muck it up.
Okay.
So let A be some vector, B be some vector, C be some real number. I have them written as two-dimensional vectors here, but the definitions work the exact same way on three-dimensional vectors.
Just adding another comma?
Yeah. Okay, so we're going to define what it means to take two vectors and add them together. This is not the addition on the real numbers. This has nothing to do with addition on the real numbers. It's just a name. I'm just calling it vector addition. Just made up that name. And what does it mean to add vector A to vector B? It means to take both their first components and add them together, and that's your new first component. And take both their second components and add them together, and that's your second component. And if they were three-dimensional vectors, take their third components, add them together, and that gives you your third components.
Is that the symbol for vector?
No. We will never write that symbol. We will just do plus like this.
Yikes.
I just wrote it that way to make it clear to you that it's not addition on the real numbers. And you will have to infer from context what addition we're talking about. And so when we're adding two vectors together, we mean this addition. We do not mean addition on the real numbers. In like manner, we will take a vector and multiply it by a number. Not multiply it by a vector, that's not what I said. Take a vector and multiply it by a number. So take some vector and multiply it by like the number 2. How do you multiply a vector by some number like the number 2? You multiply its first component by that number, and you multiply its second component by that number.
So what if you're multiplying two vectors? Would it be
We'll get to multiplying two vectors and a way of doing that. But for now, let's just make this very clear. So let's say A is a vector, is a vector 19, negative 3. And B is a vector 3, 7. Question, what is A plus B equal to? Now using vector addition.
22. And
22, 4. You did it. You just added two vectors together. Now, what is 3 times B equal to?
3 times B.
Yes.
B
We're
is
taking a number
9.
multiplied by a vector.
9,
41.
21.
What's first?
9.
9, second?
21.
Perfect. So we often call this a scalar product, and we call this vector addition. Vector addition, scalar product, because we're multiplying by a scalar. What's a scalar? Just a real number. What's a vector? Multiple real numbers in a collection. We'll only care about two-dimensional vectors and three-dimensional vectors for the purposes of this class. More definitions. The magnitude or the length of a vector.
Length.
Magnitude or length. I will use both words interchangeably.
Right.
This is how we symbolize the length or the magnitude of vector A. And it is a square root of the sum of their first component squared plus their second component squared. If they had 3 components, we would also write plus their third component squared.
Have we gone into
So we're not.
These are their components. Boop, boop. The real numbers that make up the vector. So this is the first component of vector A. This is the second component of vector A. The first component of A here is 19. Its second component is negative 3. Its first component, 3. Second component, 7.
The components are also like their shadow, like the X or Y.
Sure. We will also call this its X component and this its Y component when we're in the XY plane.
That's what it used to.
And then Z component when we talk about three-dimensional vectors.
So that's got nothing.
Look, trying to introduce that a little bit different.
The book introduced it a lot different.
Weird.
I'm going to introduce it to you much more like what you would get in a linear algebra course.
Okay. Thanks.
And that's got nothing to do with absolute value.
This has nothing to do with absolute value. It's just a symbol that we typically use for size. if you did set theory before, this is exactly the notation we use for the size of a set.
The cardinality.
Yeah.
Size.
It's somehow its size. What's the size of -7? It's like 7. Size is like how far away it is from 0. That's what we mean by like how big it is.
And magnitude just means a number.
So magnitude is just a number. Perfect. The magnitude of a vector, which is what this symbolizes, the vector's magnitude or its length is the two words I'll say. Here's how we calculate it. And we'll also just use the vector without the arrow above it to represent its magnitude.
Oh,
We
that's
will
what
do
it
this
is.
all the time.
That's what it would, okay, yeah.
And you'll have to get used to that. So what is our geometric interpretation? Our geometric interpretation is where our first component is how far we go in the x direction, and our second component is how far we go in the y direction, just like plotting a point. And so the vector 1, 2 is a vector that goes over 1 and up 2. And we draw the vector as an arrow from the origin to that point. There's the vector. That's typically how we draw it. The way that we draw the point 1, 2 is just that point. That's our geometric interpretation of the point 1, 2. The vector 1, 2 is the arrow that points to that point.
Does it have to come? I assume it doesn't have to come in order.
No, it's just typically the way we draw it. I can take that vector, and it has nothing to do with this actual coordinate system.
Right.
And so we could have drawn it anywhere in the coordinate system. We could draw it out here just floating by itself. It's just a vector that goes over 1 unit and up 2 units. And it doesn't matter where it is in space.
So it doesn't matter if it's in the negative direction or?
Well, if it were in the negative direction, it'd have to point negative.
Oh, but it doesn't matter.
So let me draw the vector really quick. -1, 2. -1, 2 would look roughly like that, assuming my drawing isn't awful. And so here's our vector d equal to -1, 2. It goes back 1 and up 2.
And then you
Yeah,
got
but the
and
origin.
Parallel.
It doesn't have to be drawn at the origin. We just typically draw them at the origin for the sake of convenience.
And we always do.
But it's just some arrow that goes back 1, up 2. This one's just some arrow that goes over 1, up 2. Stick it wherever you want in space. Here's our vector b, 3, 1. It goes over 3 units, up 1 unit. There's our vector b. Question, what is our vector a plus b equal to?
A plus b is a plus a1 plus b1.
So what is it? Here's a, here's b. What's a plus b?
4, 3.
4, 3. So there's our vector a plus b. Let's draw this geometrically. So here's our vector a. It goes over 1, up 2. There's our vector a, right?
Yep.
When you add b onto it, you're saying now go over 3, up 1. And so you could draw, starting at a, now add on vector b. And so vector b is going to go over 3 more and up 1 more. So it's going to go roughly to right there. You'll have to forgive the drawing if I am somewhat off. And there's our vector b, drawn at the end of vector a.
Right.
This now,
Is that your R?
you can't really tell that that's pink and not white, huh?
That's pink.
That was pointless, yep. This vector now is the sum of them. That is the vector a plus b. If we call a plus b the vector c, let c be a plus b, here is c. C is right there. Here was a, here was b. With me? Now it didn't matter the order that we add these vectors in. I could have started with the vector 3, 1. So I could have gone 3, 1. That gets me right here.
So you got it.
And then added on vector a, which goes over 1 and up 2. And it gets me to the exact same point.
That's so cool that it's not ordered.
Well, yeah, it's weird.
So vector addition happens to be commutative, and you can tell that from its definition here. Since addition on the real numbers is commutative, vector addition is going to be commutative.
Oh, heck yeah.
Well, it does.
Now, get intuition for what the magnitude is, or the length is. It's the length of the vector.
Right.
If I pick some vector dimensions, so we'll draw b here,
4, 2.
4, 2. So this is a vector that goes over 4 units, up 2 units. I'm going to draw on, let's just have it go like 7 units over, just so we can tell what it is. So 1, 2, 3, 4, 5, 6, 7, up 2. Drawing that vector. It's going to go over our other vectors, but here's roughly where it is, right?
Yeah.
So this is the one that went over 7 and up 2. what is the length of this vector? You just use the Pythagorean theorem. Its length, which I'm just going to call d, is equal to the square root of a squared plus b squared.
It's 49 plus
So 49 plus 4, or in other words, it's equal to the square root of 53.
Yeah.
So that would be its magnitude or its length. That's exactly what this formula gives us. It just gives us the length of the vector.
Wouldn't your C also be your length? And we did not get the C the same way.
This c
Wouldn't that be your length of A and B vectors?
no, A has this length, B has this length. What's a longer path? To go from here straight to here, or to go from here to here, and then from here to here?
That, but I'm saying the total though. So you add them, C is the length of the total.
No.
Okay, C is the length of the vector A plus B. You take A and you add B, and that gives you a vector, and C is the length of that vector. C, the length of C is not the same thing as the length of A plus the length of B.
Right.
Just because vector A plus vector B equals vector C, that does not mean magnitude A plus magnitude B equals magnitude C. Definitely not.
Why?
Because what is a bigger distance? Going from here to here and then here to here, or just going straight to here?
Just straight.
Just straight. Why? Is because the hypotenuse of a triangle, or sorry, the longest side of a triangle is never longer than the sum of the other two sides.
Okay.
That's why. Make sense?
Yeah.
That's a very good point to bring up. Just because a vector sum works does not mean the vector's magnitude works.
Okay.
Okay. So there's some examples there. More notation.
It's,
Okay. So if A is equal to this vector, then we call its first component its x component. And we will symbolize that with ax. Notice no arrow above it. Whenever we're lacking the arrow, we're talking about a real number. Anytime you see the arrow, we're talking about a vector. So a sub x is the same thing as a1. Those are the exact same thing. It's its first component or its x component. That's what a sub x is going to mean. Similarly, a sub y is going to mean its second component. And if it's a three-dimensional vector, a sub z is going to be its third component. Okay, some basic trig review because you're going to be doing a bunch of trig with these vectors. Here's some vector a. There it is. A sub x is how far over that vector goes. It's its first component. This vector went over 1 unit. Its x component was 1.
Okay.
A sub x is how far over the vector points.
Yeah, I've seen that.
Or its first component. Same thing.
Okay.
A sub y is how high up the vector points. Or a sub 2. And then a by
magnitude-
itself is the magnitude or the length.
And that's the magnitude. So the
Right.
hypotenuse is always magnitude.
Yes, when you think about it that way. If you take the vector and make a right triangle using its components, the length will always be the hypotenuse of some right triangle. It will always give you a right triangle.
Only if it's right though. 'Cause if
It
it's
will
two-
always give you a right triangle when you draw it this way. Because that's what it means. Go over that far and then up. If you go over and up, you always create a perfect right angle.
Okay.
So it'll always be a right triangle.
I've seen that.
Good?
Yep.
Now your basic sine, or your basic trig functions. So if this is our angle, then sine of phi gives you y over hypotenuse, or a sub y over a. Cosine gives you x over r,
A.
x over your hypotenuse, or a sub x over a. Tangent gives you rise over run.
Yep.
And then your inverse, or sorry, your reciprocal trig functions just give you the reciprocal.
Yeah.
You'll often be given the components of a vector and need to figure out what angle it points at. Oh, did I mess something up?
Secant.
Secant is written as AY over A, that's the same as
Sine.
Should be A over AX.
Yes.
Okay. Sorry.
I see the S and I go and I write sine again. Good catch. Sorry about that.
Okay.
But I think you all understand. Okay. So there's our trig functions. Now what's going to happen over and over again is you need to know the angle your vector is pointing at. So you're going to need to be able to calculate this phi given either the components of the vector, or maybe you know its magnitude and how far in the x direction it goes, or its magnitude and how far in the y direction it goes. And so, based off what information you have, you're going to have to calculate the angle. So how do you get the angle? Your inverse trig functions, right? If tangent of phi is rise over run, a sub y over a sub x, right? Take the arc tangent of both sides. So then the arc tangent, or the inverse tangent, of the tangent of phi is equal to the inverse tangent of a sub y over a sub x. But what happens when you plug a function into its inverse function?
It cancels out.
You get back to just your input.
Right.
And so that gives us that phi, then, is just equal to the inverse tangent of a sub y over a sub x. So phi is equal to the arc tangent of a sub y over a sub x,
Also,
or the arc sine of a sub y over a, or the arc cosine of a sub x over a.
obviously. The inverse function is just the domain and range swap. Am I thinking of that right?
It's you swap the domain and range, and you also need to run the mapping backwards.
What do you mean about that second part?
Run the mapping backwards.
Yeah.
If y is equal to f sub x, then f inverse of y is equal to x. That's what I mean. So make sure you run the mapping backwards.
Okay.
But yes, in the process, you swap the domain and the range. Okay. So there's some basic trig. You're going to have to use this trig over and over and over again. No way around it. Messing with the vectors, figuring out what angle they point at, or else knowing what angle they point at and what their magnitude is, finding these components.
Right.
So you're going to go back and forth like that. Probably should have given you guys a trig worksheet solving a bunch of triangles. I've got one from intermediate algebra. That probably would be good. Maybe I'll make that your quiz for next week.
Scary.
Scary. Make sure I print one out before the class is over and we'll hand them out. Okay, so now let's move on to more example problems. Our next example problem is going to be, sorry, I know that's a mess, 1.5. Okay. We'll just clean all that up, and then, oh, we can't really clean all that up, can we? Because I'm not done over there. So I'll clean up this side, not for us to read the problem, and then we'll go for it. Okay, so we're on example 1.5 here. A cross-country skier skis 1.00 kilometers north and 2.00 kilometers east. Let me just draw the picture to the side as we're doing this. Very useful to always just draw the picture as we go. So they went, typically we always set it up so that north is up, east is that way, south is that way, and west is that way. Very convenient because we're actually facing north. Okay, so the skier goes 1 kilometer north, so that was 1 kilometer, but with 3 significant figures, and then 2 kilometers east.
Reaching out good.
How far and in what direction is she from the starting point?
Should be fairly simple.
So yeah, this is just going to be using basic trig.
So it's 5 square root 5.
So yeah, her distance is, she is square root of 5 meters. Now be careful, we can't leave it like that. Remember, we have to write that as 3 significant figures.
Right.
3 significant.
You're not in a math class anymore. You're now in a physics class. And so significant figures now matter very much. So square root of 5 on your calculator, whatever that comes out to.
2.7.
How does square root 5 get here?
2 squared is 4. 1 squared is
Gotcha.
So you got square root of 5. Comes out to 2.24 when we round. So 2.24 entire meters, meters. So that's how far she traveled and in what direction. Now in what direction? Sorry, what?
Your units. She kilometers.
Oh, kilometers, thank you.
Oh.
Okay, good. And now, what direction does she point?
So it'd be from the angle.
Now, yeah, but we need to either find this angle or we need to find this angle. And we can say she's this many degrees east of north. Here's north, here's east.
That's 90 right there.
Or we can say she's this many degrees north of east.
But yeah.
So, do we want to find this angle or this angle? Doesn't matter, just
You
pick
have-
one.
you have the-
Top or bottom?
Well, top. We have top. It's fine.
Top, we have top.
No.
We also have bottom, because this is just one.
No, but let's just use that one.
So, we'll find this one first, I guess. This one, theta.
Okay.
So, first and foremost, be careful. Redraw your triangle so that it's like this, like you don't mess yourself up. Here's your right angle, here's theta. This is now 2, this is 1. So when you're going to do this, theta is equal to the arctangent of 1/2,
Whoa.
Yeah.
right?
Yes.
Because rise is 1, run is 2.
So you're just gonna use the inverse function that is easiest with your triangle?
Not 1/2.
No, that's
2, 1. Relative to this angle, my rise is 2 and my run is 1. That's why I redrew it this way down here. That is a big mistake you're going to make over and over again.
Yeah.
Why can't
Okay.
you use one of oh?
Arctangent.
Never mind. Okay, I got you now.
How do you evaluate arctangent of 2?
Arctangent of 2, you pull out your calculator,
Oh.
you hit your arctangent button, 2, and parentheses, and it gives us 63.4 degrees when we round to 3 significant figures.
Why did you flip it?
Well, I just wanted to make sure you did the math right. Relative to this angle, our rise is 2 and our run is 1. That's why I redrew it like that here.
Right.
The sine of this angle is opposite over hypotenuse. The tangent of this angle is opposite over adjacent.
Okay.
It's 2 over 1. It is not 1 over 2. That's the mistake you guys are going to make a bunch of times.
How does that make sense? Why can't?
It doesn't matter how you draw the triangle. Here's the triangle, I redrew it like this.
Yeah, okay.
You're just always used to thinking about the triangle oriented this way. If you're going to get confused, redraw your triangle so that your angle's on the left-hand side, your right angle's on the right-hand side, and work out your math that way.
Oh, I see now. Okay.
Okay,
I picture.
now we could have also looked at this bottom angle phi, call that one phi, and what would phi be? Phi would be the arctangent now of 1 over 2.
Yes.
Because now in that case, relative to this angle, our rise is 1 and our run is 2.
Yeah.
And that comes out to roughly 26.6 degrees. Which I doubt, because these two together have to add up to 90.
Yeah. Okay, that makes sense.
And so your answer can be, it's 63.4 degrees east of north. So start out facing north and turn 63.4 degrees east. Or you could say it's 26.6 degrees north of east. So start out facing east and then turn 26.6 degrees north.
North of east, not east of north.
You can turn this far east of north,
Why?
or you can turn this far north of east. Look, if I'm facing north and I turn 70 degrees, that's the same as starting out facing east and turning 20 degrees.
Yeah, that makes sense. I'm saying I don't know why they word it how they do, but that makes sense.
So it's got to be one of those. And we'll see how they write it out. They say 26.6 degrees north of east. So they chose to use that one. Oh, they also say 63.4 degrees east of north. So either answer is perfectly acceptable.
Okay, sweet.
So that was,
Vectors, did they come up with that problem at all? I feel like we didn't solve that problem using any of the. I guess we did.
we just used that basic trig over there.
Yeah.
Okay, so next one is finding components. Let's erase here. So what are the x and y components of vector d in our figure? So they give us some figure down here. So vector d is this one. What are x and y components of vector d if its magnitude is 3.00 meters? So we know d's magnitude is 3.00 meters, 3 significant figures.
Yeah.
And alpha is 45 degrees.
So just draw a triangle and figure it out.
Yeah, so we can look at what they have here, or we can look at,
Why don't they draw so weird?
well, the sign matters. So sanity check, your y component's going to be negative, your x component's going to be positive.
Yes.
Why?
Because it's pointing down like that. Just like this point in the xy plane,
How do you know it's pointing down?
Because it's the negative.
they're saying use the picture.
Oh, based on which?
Yeah. So they said based on the picture and the picture showing it drawing down.
Okay.
Okay, so now, what is its x component going to be? Let's draw that vector d right here.
Oh, dx.
This right here we know is 3, and this angle right here we know is 45 degrees.
That's dx up there.
What is this distance?
Dx.
Dx, and how do you calculate that?
You can do trig.
Trig. How do you calculate your x component?
You use one of those.
Yeah, you use one of these. And so, if cosine of our angle is a sub x over a, then a sub x, just looking at that equation, is equal to a cosine of our angle.
Obviously.
So here we want d sub x. D sub x is going to be equal to d, or 3,
Yeah.
times the cosine of our angle,
Which is 45 degrees.
which is 45 degrees.
Which is.
So this is root 2 over 2, but then we got to multiply it by 3. So 3 root 2 over 2, but to 3 decimal places.
Okay, I see.
Oh, wait, our angle, 45 degrees, did they say 45.0? Be careful. 2 significant figures, not 3. Our angle is only known to 2 significant figures. So we got to be careful there. So this is 3.00 times the cosine, cosine of 45 degrees, and so it should be 2.1 meters.
So you use root 2 of 2.
Well, no, you can just plug it in your calculator just like that. So this is a math class, so we don't want precise numbers anymore.
Oh, right, yeah.
We want approximations. And then it's the exact same thinking here, except for you use sine rather than cosine, and it's going to come out to 2.1 meters as well. So whatever their answers are, 2.1 positive minus 2.1 for the y. We didn't specify that, did we? So d sub x, just writing it all out, d sub x is equal to 2.1 meters, and d sub y is equal to minus 2.1 meters. We're using notation that the author doesn't use, but we could say vector d is equal to 2.1 minus 2.1. Meters.
Yes.
I like that a lot better.
I think he'll eventually use this notation. I don't know why he's afraid of it.
It looks so much prettier.
But so the x component, the y component, there it is. Okay, any questions on that?
Don't make sense.
Oh,
Part B.
what are the x and y components of vector e here in this figure? The magnitude of the vector is 4.5, and the angle beta is 37.0 degrees. And now they're just drawing it on a weird angle, just like you don't get stupid, simply because your picture doesn't line up nicely. When you take beginner physics, remember, you pick the reference frame most convenient for your problem. And it's not always going to look like this. This could be your reference frame. So it's saying that's the positive x direction, that's the positive y direction.
That sounds pretty simple though.
Yeah, so I'm going to redraw that angle just in a picture frame that helps us think about it. It's beta, or roughly 37 degrees away from this, so it's going to shoot up something like this. Here's E in our positive direction. What's its length?
Wow.
4.50, and the angle here now, we could use 37 for that angle, but I'm just going to use this angle instead and call it what? 57? Or 53, I mean?
Yeah.
So this is 53 degrees.
Okay, so
Nothing special about what 53.0 degrees.
we just reoriented that picture.
Just if it helps us think. We could have reasoned about it right here, and I'm going to do both. So first doing it what might be the easier way. Now, what's e sub x equal to?
1
it's just 53, it's just whatever E is, times the cosine
53.
of 53 degrees.
E was 4.5.
So you go ahead and plug that in. E sub y is just going to be E times the sine of 53 degrees. And I'll really quick plug that one in.
Cosine is 2.7.
All right, give me a sec.
So 3.59.
Is it the cosine? E
Cosine
of
for-
y is a cosine, isn't it?
No,
Because
y
of
is-
how it's set up.
If I would have used this angle, it would have been. I decided to orient it using this angle. So this is our y, this is our x.
But the angle it gives you is the one off of E of y.
I know, and I chose to use 53 degrees rather than the one they gave me. So I chose to use this angle.
Oh.
So you're thinking right, but just not what we did. So let's see, my number came out to 3.59, and yours came out to,
Cosine?
yeah, or cosine, right?
Cosine is 2.70.
2.70 when you round it. Let's really quick check. I know it's a mess here, but they got to have it somewhere.
2.71.
2.71, 3.59.
I forgot to round. It should be
Oh, you didn't round, but you did it right. Okay, now let's redo the problem, just messing with the picture. Okay? So our y component here, when we look at it, is going to be, notice that that's using the adjacent. So this is going to be using cosine if we use this angle here.
Yep.
So this side right here is going to be E cosine of beta, and this side right here is going to be E sine of beta, if you want to just work with the picture directly. And if we were to calculate that out, we get the exact same thing. I'll do the cosine, you do the sine.
Okay.
So I forgot what E was, 4.5.
Sine of 37.
Was it
Yes,
37?
37.
Yes, you're correct. And so once again, I got the 3.59.
I got 2.71.
Okay, 2.71. So you didn't have to swap it and think about it that way. I'm guessing a bunch of you are going to make mistakes not doing that. So
Yeah.
both ways work. It's the same thing, however you want to think about it. You have to do a lot to master our trig now that you're in physics.
Yeah.
Okay, what example is that? 2.16. Let's move on to example 2.17, I think.
Okay, what?
What?
This is 1.1.
Sorry.
What?
I have no clue where the 2 came from.
I lied.
Okay, 1.7. Here we are. This problem. 3 players on a TV reality show are brought to the center of some large flat field. Each is given a meter stick, a compass, a calculator, a shovel, and in different orders for each contestant, the following 3 displacements. So you're supposed to go that many meters, 32 degrees east of north, that many meters, 36 degrees south of west, that many meters due south, and it's supposed to take you to some prize buried in the field. You got to be the first one to try and find the prize in the field.
Porsche.
Okay? The author took the time to roughly draw out what this is going to be. This, and this. So rather than following that path, you could just add all 3 vectors together and then go to wherever the resulting vector tells you to go. To add the vectors together, remember with vector addition, we need their components. So I need to find the x and y component of this vector, the x and y component of this vector, the x and y component of this vector. Once I do that, then I can quickly sum to figure out what r is here. You with me?
Yeah.
So let's figure out what a is in terms of its components.
How do you do that?
Shoot. Fractals.
We're going to be using basic trig. So
What is A though?
So they tell it to you right here. A is 72.4 meters, and it's 32.0 degrees east of north.
Right.
Oh, so you have to break it into
So you,
three.
right, so you start our picture like this. Our vector is 32 degrees east of north. You start north and go 32 degrees east. And its length is 72.4. So this is 72.4. This angle right here is 32 degrees. Or this angle right here, if you'd rather think about it that way, is 58 degrees. Which this will probably be the easier angle to think about.
Right.
Yeah.
Okay.
And now we need to break this vector up into its x and y components. So we need to find this distance and this height.
Yeah.
Yeah.
Now I can do 72.4 times the cosine of 58 degrees to get this.
Yeah.
Or 72.4 times the sine of 32 degrees to get this, which is this. Whichever way we want to go.
Which is 58.
So using the 58, we need 72.4 times the cosine of 58 degrees. One of you plug that in. And then we need 72.4 times the sine of 58 degrees. And I'll plug that one in.
What does that give you?
72.4 times the sine for the height
Yeah.
of 58. So that's 61.4.
Cosine was 38.4.
Oh, I wrote that in the wrong spot. So let me see. Mine was 61.4. Yours was what?
38.4.
Did you do the cosine?
Yes.
So there's vector A split up into its components.
Okay.
Now we need to do vector B split up into its components.
And then
Uh,
Yeah.
oh, do we have 4 significant figures?
Do we?
3.
No, no.
We only have 3 significant figures.
72.4.
They wrote it in 4 for whatever reason. I guess you probably want to round when it's all said and done.
I
So-
got it.
So give me yours to 2 figures, or to 4 significant figures.
It's 38.36.
36, and mine was 61.40. Okay. So our final answer we'll only write in terms of 3 significant figures or whatever, but just so we're matching up with them, they got 38.37. They're saying you rounded wrong, and 61.4.
38.36. Oh, well, I guess if you round your 6 up, it's 38.37.
Yeah.
Oh, sorry.
Okay. So there's our x and y components for our first vector. Now let's do it for our second vector. Our second vector points 57.3 meters, 36 degrees south of west. So we start west and we shift that 90 degrees south. So here's west, shift 36 degrees south, and now we're something like, that was more than 36, but who cares? Okay, so there's 36 degrees. The length of this vector is
90, whatever.
57.3.
57.3. And now we need to find its x and y components. Right?
Yep.
So our x component here is just going to be 57.3 times the cosine of 36. So 57.3 times the cosine of 36, and that comes out to, this was for vector B, this first number is going to be 46.36. Now, why am I wrong already? Sanity check. Why is my number insane? Why is my x component for sure not 46?
Because you're in the negative direction.
Because we were in the negative direction, so it should be negative 46.
Okay. I thought it was crazy for a second.
And our y is also going to be negative because we're going down. Okay. And so for the next one, we got switch our cosine out with
33.68.
and we get 33 point. Oh, thank you. Okay, so there's our x and y components for that vector.
That's a negative, right?
Oh, thank you. That was a test.
That's quadratic.
You got 1 bonus point that doesn't count. Okay, and then finally for vector C, this one's already in terms of its components. Because they said 17.8 meters due south, straight down. So that's 0 in the x direction and negative 17 point what? 8. And so now we add all those up, and that's going to give us our vector R. You do the x's, I'll do the y's.
Does it just be capital R or lowercase r?
Whatever it showed on there.
Okay, so we need to add up the x's and y's.
Yep.
How would we?
All of
It's
them?
negative 7.99.
So you added up all these, and you got what?
Negative 7.99.
Negative 7.99. And when I added up all these, I got 9.92.
Is that reasonable?
And that's exactly what they have, that in the x direction, that in the y direction. So now, we got to tell our contestant where to go.
Okay, one second. So just to recap, this R vector is the
Capital R here is the sum of these three vectors. I did this vector plus this vector plus this vector.
What does R stand for? Is it
Just a resultant vector.
oh, so R is okay.
R is the sum of those three vectors.
Angle
and it's a vector itself.
by doing
So now we need to tell our contestant where to go.
That's where the R is.
That is where
so
it goes.
-7.
Kind of. But we don't want them to walk 7.99 units in the x direction and then 9.92 units up.
just died.
We want them to be able to just turn with their compass and start walking in that direction.
Sounds like some Pythag.
So we need to tell them how to turn, and we need to tell them how far to go. Now, what is R? R is how far to go. R is going to be the square root of this squared plus this squared. Of -7.99 squared plus 9.92 squared.
And you get 12.7.
12.7.
That's really convenient.
Okay, so this comes out to 12.7 meters.
And that's our magnitude, right?
That's your magnitude. So I'm telling you, walk 12.7 meters. Now we need to give them the direction. So
Oh,
we need to somehow figure out what this angle is or what this angle is.
why?
We can pick whatever angle we want to tell them.
Just give me the portion. Okay.
So
Gotta burn your portion.
draw this in here. Which angle should we find? Should we find this one or this one?
The bottom one.
The bottom one. So if we're doing the bottom one, we need to rise over run.
It's easy. Do we have
So the rise is 9.92 and the run is 7.99.
-7.99.
Well, we're drawing our triangle right here. Ignore everything else for a second.
Okay.
Rise over run to give us this angle.
Okay.
So no negatives, you're saying?
So there's not going to be a negative.
Why?
So,
Why is that?
well, if we could find this angle if you wanted, and then view the rise over run as negative.
How does that change?
But then you have to worry that it's not accidentally giving you this angle down here. And you have to remember back to your trig, what is the domain of the arctangent function? And you're going to confuse yourself thinking about it that way.
1 or 0?
So I think it's way easier to either find this angle or find this angle and reason about it from there.
Yeah, that's what we're doing.
So our rise for this triangle is 9.92 and our run is 7.99.
Why is that not negative? Why is that not negative?
Because we're just messing with this triangle. This triangle is this triangle. I could flip it and put it over here, it doesn't change anything. Ignore all our coordinate axes.
Okay.
Because we're not finding the slope of this line in our xy plane. We're finding the slope of this line relative to just this triangle. I'm not trying to get this angle, which is what the negative would try and give me. Let me do both for you really quick to show you what it's giving you. So first let's do the arctangent of the way you want to say it. You want to say 9.92 divided by negative 7.99.
Right.
And what that's going to give me is negative 51 degrees. Negative 51 degrees is this angle. If you were to continue this line, that gives you this angle.
Oh. Wait. Okay.
If you keep it positive, then the only difference is it would just be 51.15 degrees right here. So 51.1 degrees there. Both are fine, just understand what it's giving you.
That doesn't make
That's
sense.
so strange. Why that? Okay. Okay.
Okay, so we can tell them to go 51.1 degrees north of west.
Yep.
Start west, remember?
Right. So in terms of how they're going to do this,
39 degrees west of north. So this one. Maybe the other.
okay, so they want to do west of north. So they want to do this one. And they did 39 instead of 38.9. So they only used 2 significant figures. And I don't know why they only used 2 significant figures. They should use 3. So they are calling this 39, which is what we would get if we only use two significant figures. But it should be 38.9, unless I'm missing a point where we only had two significant figures. We had this angle to, did one of our angles only come to two significant figures? They're all three, so I think that's a typo in the book. That or I'm missing something. So either we're right or we're wrong, guaranteed. Okay, 1.8. After an airplane takes off, it travels 10.4 kilometers west, 8.7 kilometers north, and 2.1 kilometers up off the ground. So this is a three-dimensional vector now. Help me out here. How far north?
8.7.
So we're going 8.7 up here. Oh, did it give us, let's see, which way did it tell us first? West.
West.
So we're going 10.4 this way. And then what was it?
8.7.
8.7 this way. Are these miles or kilometers? Kilometers. And then 2.1 up out of the board. I don't know how to draw that.
Yeah, I was gonna say.
So instead, I'm just going to say my resultant vector has components in the x direction. We'll say it went negative 10.4. In the y direction, it went 8.7. And then up into the air off the ground, it went 2.1. Now they're going to ask us how far has the plane traveled, right? What's the magnitude of its displacement, or in other words, how far did it go? Well, it's just going to be the magnitude of this vector. And so if this is, this is what our vector is. So r is just the Pythagorean theorem in 3 dimensions. So this is just the square root of our first component squared plus our second component squared plus our third component squared.
Magnitude is that, okay.
Yep, that's the magnitude of a 3-dimensional vector. First component squared plus second component squared plus third component squared, all under the radical.
Fine, that makes sense.
And it comes out to 13.7 kilometers.
Good
Was
math.
that it?
Yeah.
That's all wrong.
That's how far the plane has traveled. Sandy check, it better be a bit longer than any of these, otherwise we for sure messed up.
Why?
Because these are its components. The same reason that the longest side of a triangle, the hypotenuse of a right triangle, has to be longer than any of the other two sides.
Okay.
This is the hypotenuse of
Three-dimensional.
a right squared sort of looking thing. You could make a right triangle in there, but that's not exactly what's following. Yeah.
Sort of. Okay.
But the point is, well, there it is.
Like
Okay.
Diamond cut.
So you know how to do that now. So on your next quiz, calculate the magnitude of a vector, right?
Fire.
Yep.
Okay. And then we stop now and talk about unit vectors. Okay, so back to lecture for a little bit until we go forward. So a unit vector is a vector that goes 1 unit in a particular direction. So either 1 unit in the x direction, or 1 unit in the y direction, or 1 unit in the z direction.
So it's a secular? What's that?
A scalar? No. It's 2 numbers. So we have a special name for these vectors because they come up so much. We use them so often. So I hat is a vector that goes 1 unit in the x direction.
Dude, why do we use hats here in model?
And not an arrow above it. To let you know that this isn't some vector I. This is the unit vector I.
What's the difference between the unit vector and the
Give us.
A component is just a number. If I say A is equal to the vector A1, A2, A3, a 3-dimensional vector, you with me?
The magnitude of that, okay.
Oh, sorry. That's our vector A. Good catch. If we were to calculate the magnitude, A would be equal to the square root of A1 squared plus A2 squared plus A3 squared.
Yep, okay.
So there's A as our magnitude. A sub x, our x component, is just a number, A1.
Yeah.
It's not a vector.
Yeah.
Okay, I can also now write A as A1 times I hat plus A2 times j hat, the unit vector in the y direction, plus A3 times k hat.
That doesn't make sense. Where are you? What is that equivalent to, you're saying?
This is another way of writing this exact same vector. Your author favors this over this.
Why?
Well, he does. So let's just draw this out to try and make some sense out of it. Try and draw 3 dimensions. So here's our x, here's our y, here's our z axis.
Okay.
With me?
Yeah.
So I hat is a vector that points 1 unit in the x direction. So that's I hat. J hat is a vector that points 1 unit in the y direction. That is j hat. And k hat is a unit vector that points 1 unit in the z direction, k hat.
And what is this saying?
Well, first off, just know that that's what I hat, j hat, and k hat are. So I just plotted them. I hat goes 1 unit in the x direction, 0 in the y, 0 in the z.
I is x.
I goes x. What are the order of the letters? I, j, k, x, y, z.
Oh, sweet. Okay. That makes
So
sense.
easy to remember. So 1 unit in the x direction, 1 unit in the y direction, 1 unit in the z direction. You see that?
Yeah, I see that. But what's the point of that? Like,
Okay.
what is that trying to say?
So now let's go in 2 dimensions because this will be easier to see for a second. Give me some vector in 2 dimensions.
Vector.
Yeah, we'll say vector b, give me some 2-dimensional vector.
3 and 2.
3, 2. Okay. So here's one way I can write vector b. It's 3 units in the x direction, 2 units in the y direction. It's this vector.
Okay.
That's one way to write it. Good?
Yeah.
Now notice, if I use this notation for vector b, what am I going to say? I'm going to say vector b is equal to, what was my first component?
3 times 1.
3 times I hat. I hat is a vector. It's a particular vector.
If it's a vector, why can put the...
Just stick with me for a second here. Plus 2 times j hat. You with me?
Yeah.
Now, so b is equal to 3 times I hat is a vector. In this case, it's a 2-dimensional vector. So 1, 0. Plus 2 times the vector 0, 1. You with me?
Yeah.
How do we do a scalar product? A number times a vector, we just multiply both the numbers inside by 3.
Yeah.
So this is b hat is equal to 3 comma 0 plus 0 comma 2. Which add those together, get you back to the vector 3, 2.
Okay.
So
Yeah.
3 I hat plus 2 j hat is the exact same thing as the vector 3, 2.
Right, that makes total sense.
Why does it exist though?
It's just a way to write it in terms of unit vectors. Now, here's another way that you can think about this. Let's draw I hat in our picture. Here's I hat. There it is.
Okay, that's...
We're saying B is take 3 I hats. 1, 2, 3. Now add on 2 j hats. 1, 2. Our vector is 3 units in the x direction plus 2 units in the y direction. It's 3 I hats, 3 unit vectors in the x direction, plus 2 j hats, 2 unit vectors in the y direction.
Okay, so the concept makes sense, it's just the point of it doesn't make sense.
It's just notation. So our author does not use this notation or introduces it later. Here is a notation he's going to use.
That's so strange. Okay.
Yeah, you like this notation better, don't you?
Way better, it's way easier to understand.
What is
The
there
I
a
hat,
practical
J hat,
reason
where
for
did
it?
they even pull that from?
Just let you write it as an equation.
It's so random.
I guess it kind of makes sense.
It's useful having unit vectors. And you haven't account 3 yet, but you use unit vectors all the time, and you do like a change of, when you pick a reference frame, it's like you're changing what your unit vectors are. Switching from one reference frame to another reference frame. And so it's very nice for transitioning from one perspective to another perspective. But it doesn't matter. It's common notation. It's useful notation. You don't like it, you're going to have to get used to it. And you'll learn to love it.
Okay, the concept
You'll
makes
learn.
semi-sense, so.
Okay, so I hat, the vector 1, 0 if we're in 2 dimensions, and j hat, the vector 0, 1 if we're in 2 dimensions. If we're in 3 dimensions, I hat is 1, 0, 0, j hat is 0, 1, 0, k hat is 0, 0, 1. Make sense?
Okay.
And so notation, I can write my vector A as its x component times the unit vector in the x direction plus its y component times the unit vector in the y direction.
0, 1, and then 0, 0, 1.
Sure. So now I can write my vectors that way. So different ways of writing the vector. Okay, so with that, let's move on to exercise 1-9. So, example 1-9, it gives us these two vectors. D is a vector that's 6 units in the x direction, 3 units in the y direction, and negative 1 unit in the z direction. Right?
Yeah, that's okay.
And E, 4 in the x, negative 5 in the y, 8 in the z.
I can read that.
Find the magnitude of 2D minus 3E. So we've got to scale this up twice, scale this up by a factor of 2, and then subtract E from it.
Okay, so that's like.
So let's scale this up by a factor of 2. So 2D is going to be equal to,
12.
we're going to have 12 I hat plus 6 j hat minus 2 k hat, right?
And you're not going inside the hats and doing anything.
Yeah.
The 2. So those are off limits.
Well, they're just the same as what they were before.
Okay.
And now I need to subtract E. What's 12 minus 4?
8.
So I'll write R here, our resultant vector, is going to be 8,
1.
1, no, we're subtracting. What's 6? Take away negative 5.
1.
11.
Okay, what?
If you have $6 and I get rid of $5 of debt, it's like you got $11 now.
Minus 5, minus negative 5.
Subtract negative 5. Over here, you did 12 minus 4. Over here, you're doing 6 minus negative 5.
Oh, because we're subtracting from E.
We're subtracting E. We're not adding, we're subtracting.
Okay, I was like,
Okay.
What is going on?
And now negative 2 take away 8 is
10.
minus 10. Okay, and they want the resultant vector here, right? So we're going to be looking at 8 squared plus 11 squared plus negative 10 squared all under the radical, which will give us the magnitude.
Why are we squaring it? What are we trying to find the...
We're finding the magnitude. So this is, to write it, this is R. We're looking for R.
Magnitude of that.
The magnitude of the vector we get. 2 of this vector minus 1 of that vector, the result's going to be a vector. It wanted the magnitude of the vector.
So we turn it into a diamond. And we
Wait.
make the diamond in
If that makes sense to you.
half. It does, because it makes a diamond when you shoot out.
Okay. So 8 squared
17.
plus 11 squared plus 10 squared. Oh, missing parentheses.
It equals 16.9.
16.9 to 3 significant figures, which is
16
what we have. It's 3 significant figures, right? And that's what they say, 16.9 meters.
Meters.
Okay. Yes, meters, very important. Magnitude is that many meters. Number by itself is meaningless. Okay. So that was 1.9. Now let's talk about multiplying vectors together. So we've talked about vector addition and adding vectors together, and we've talked about taking a vector and multiplying it by a number. Now we need to talk about taking a vector and multiplying it by a vector.
This is no clue.
Huh?
It's one of the few parts reading last night that I had no clue.
We're talking about scalar products, we're talking about vector products right now.
So we already talked about vector addition and multiplying a vector by a real number. We have not talked about multiplying 2 vectors together. Right?
Yeah.
So, let's go ahead and let A be the vector, A1, A2, A3, and B be the vector, B1, B2, B3.
But if we were turning that to the hat thing, it would be bx I hat.
So it would be
Or plus.
A sub x I hat plus A sub y j hat plus A sub z k hat.
Okay. Yeah, that's it.
So definition. What do we mean by vector A times vector B with a dot right there? We're calling this a dot product. This has nothing to do with multiplication on the real numbers.
Okay.
It's just a name. I'm making up an operation. And I say, when we do this, here's what I want it to mean. I want it to mean A1 times B1 plus A2 times B2 plus A3 times B3. You can't stop me. I can define whatever I want. That's what I want that to mean.
Okay.
It's just a definition. Notice that the way I've set this up is when you take what I'm calling the dot product of two vectors together, the result is just a real number.
Yeah.
But it's not a vector.
So it's also called the scalar product too, right?
No, scalar product is when you multiply the vector by a scalar. So scalar product was something like 3 times A hat. Or the vector A.
So it's going to be a
Because you
scalar.
multiply by a scalar. This is called the dot product, is what it's typically referred to.
And it comes out as a scalar.
And it comes out as a scalar, as a real number. Just a number.
Not a magnitude.
Huh?
Not a magnitude.
Not a magnitude.
Okay.
There's just this definition. Now it just so happens, something to observe, that when I take A hat and I dot it with itself,
A hat. The vector A.
sorry, yeah, thank you. When I take the vector A and I dot it with itself, what do I get?
A squared. Or
A1 squared plus A2 squared plus A3 squared. You see that?
So you get its magnitude squared.
So I get its magnitude squared. So this is the same thing as its magnitude squared, or in other words, it's equal to its magnitude squared.
well, what?
Yeah, right.
Because you take the square root, and that just gets you your magnitude. Which is
What is the magnitude? It's the square root of A1 squared plus A2 squared plus A3 squared.
So how do you have a?
So A squared gets rid of the square root. The magnitude isn't equal to this. The magnitude squared is equal to this.
So
What is the magnitude of A? It is the square root of A1 squared plus A2 squared plus A3 squared.
yeah, A is the magnitude of that.
That's what A is.
Yeah.
So what is A squared equal to? Square both sides. When I square this, and when I square this, I get rid of the square root, and you're left with just that.
Yep.
Okay, but what?
So a vector dotted with itself is the same thing as the magnitude squared.
Makes total sense.
Okay. I think it makes sense.
Okay, now why on earth, in naming this thing, would I call it a product?
Because you're product counting?
Because it happens to be distributive.
Oh.
So let me kind of show that to the side really quick. When I do vector A dotted with vector B plus vector C, this is going to just be equal to vector A dotted with B plus vector A dotted with C. That's the only reason we're calling this a product, is because it just so happens with how we define it, it distributes. Now I'm going to prove it distributes, so I'm going to mess with this and keep messing with it until it looks like this. You with me? I'm going to prove that this is equal to this.
Okay, that's just normal, though, right?
Yeah.
That's what normally happens with scalars.
This is what normally happens with products. If it's a product, it in some sense should distribute over addition. So the reason we call it a dot product is because it happens to distribute this way.
Yeah, but that's how scalars distribute.
Yes.
Okay.
The real numbers, the multiplication on the real numbers also distributes this way using the addition on the real numbers. This is all vectors, no scalars involved.
I know, but the functionality is.
But it functions the same, which is why I need proof.
Okay.
Okay, assume that A here is a vector. We'll do 2 dimensions, A1, A2, B1, B2, C1, C2. Just for the sake of not having to write a ton. Okay, so writing this out, what are we doing here? We are talking about the dot product of A1, A2, writing out this vector, and we're going to dot that with the sum of these two vectors. You with me? So I'm going to add these two vectors together. That would be b1 plus c1, comma, b2 plus c2. Just what you would get adding
Oh, yeah, yeah.
those two vectors together. Pretending that these are the vector a1, a2, b1, b2, c1, c2.
Yeah, okay.
Just two dimensions so I don't have to write as much. Okay, now let's do the dot product. What is the dot product between two things? It's this times its first component added to this times its second component.
Okay, what happened?
That's exactly what our definition is.
So,
It's the first thing in here multiplied by the first thing in here plus the second thing in here multiplied by the second thing in here. And if it's three-dimensional, the third thing in here multiplied by the third thing in here.
yeah, but you don't have that over there.
The first thing in here multiplied by the first thing in here. So we don't need this parentheses anymore. We added it together. So we're just dotting these two vectors. b1 plus c1, that's just a number. I could call it d1 if I wanted.
Okay, yeah, that makes sense.
So this is now equal to a1 times, now times on the real numbers, b1 plus c1, comma, and this is equal to a2 times, now the time on the real numbers, b2 plus c2. Because inside the vector, these just real numbers, just real numbers, just real numbers, just real numbers. You with me?
Did you distribute before? Oh, you added then distributed.
I just calculated the dot product.
Okay, I see what's going on. Okay.
Just calculate the dot product. And now, because now this is multiplication on the real numbers. Since multiplication on the real numbers is distributive, this is equal to a1 times b1 plus a1 times c1, comma, a2 b2 plus a2 c2. Right?
Yep. Okay, that makes sense.
Now this is the exact same thing as the vector a1 b1, comma, a2 b2 plus the vector
A1
a1 c1 plus a2 c2. Which this is the same thing as
Vector A times
a1 a2 dotted with b1 b2. Oh wait, what did I mess up?
You just jump. Why can't you just jump? Oh. Okay.
What did I mess up?
Oh, you put it in a.
When I calculate my dot product, it's no longer a
Yeah, it's
vector
no longer.
because it's just a scalar.
Whoa, what happened?
When you calculate a dot product, the result is just a scalar. It's just multiplying and adding numbers together. It's no longer a vector. A1 or A dotted with B is just a bunch of numbers multiplied and added together. No longer a vector.
Why?
By definition, here's its exact definition.
Oh.
So this, by definition, gives us this, which is equal to which is equal to
But why would that change? Oh, you get rid of the commas?
plus, yeah, it's all scalars. Plus, did everything I do so far make sense?
So you just got rid of the commas.
This times that plus this times that. Distributed, there it is. Now we got that. Okay, now a1 b1 plus a2 b2. That's the same thing as a1 a2 dotted with b1 b2. Right? If you take the dot product of these two vectors, it's that times that plus that times that. That's this.
Yep. So you just you like factored it basically.
Sure. It's one way of thinking about it.
Okay, alright.
You see it?
Halfway.
We're going back and forth between vectors and real numbers.
Yeah, you're reversing the definition.
Right, reversing the definition. It's like, ignore that part for a second because it's two-dimensional. This is the same thing as that in the two-dimensional case.
Oh, okay, yeah, I see.
Yep.
I see.
Same thing over here. This is the exact same thing as the vector a1, a2,
And then C.
dotted with c1, c2. Okay, and finally, just writing it the way we know and love. That's the same thing as vector A dotted with vector B plus vector A dotted with vector C. Okay, so whoa, look at that.
Wow.
It distributes the way we know and love. Beautiful. So that's why it's called a product. And when we talk about the cross product, it also distributes, but I'm not going to prove that the cross product distributes. So, giving you a little bit of a taste for it. Now, your author is going to tell you that the definition of A1, or vector A, dotted with vector B, is going to be the magnitude of A times the magnitude of B times the cosine of the angle between them.
What?
You didn't read that part?
That's how your author is going to define these things. I'm going to prove to you, here's how everyone in the world defines it. Here's how the author chose to define
He
it.
uses such a weird way of doing it.
He picks the most convenient way. I'm going to show you that the way that everyone else defines it is the same as your convenient way. He also points out this happens to be the same way, and he proves it by kind of cheating. But, yeah.
That's so dumb.
Oh,
Okay.
it says
So now I'm actually going to prove it.
Alright.
You ready? So to prove this, I need to remind you of your law of cosines. If you have a triangle, any triangle, where this is side length A, this has side length B, and this has side length C, and this is some angle theta, then C squared is equal to A squared plus B squared minus 2AB cosine of the angle opposite side C. And I proved that for you back in calculus when we did our trig review. It's not a terribly hard proof, but not going to take the time to do it today. It's a general form of the Pythagorean theorem. Notice that if this happens to be a right triangle, the cosine of 90 degrees is 0. So that term goes away, and so you get A squared plus B squared equals C squared.
Oh, that's right.
Gotcha. Okay,
So it's
I
the
remember.
general form of the Pythagorean theorem.
Yeah, okay.
That's what we're going to use. So I can prove to you that A dotted with B is in fact this thing. All right, so let's just draw a random vector A. Maybe give myself some space here. Here's vector A. Here's vector B.
Is this saying the magnitude of A plus
Yes,
B?
magnitude of A times B.
Magnitude of A times the magnitude of B times the cosine of the angle between them. Now this vector, which points from A to B, is going to be the exact same thing as vector B minus vector A.
What?
Oh.
This is going to be the vector that points from here to here is the same thing as vector B minus vector A.
Right. Yep.
Your start, or your end minus your start, gives
Okay.
you your displacement.
Okay.
Good? Do you just kind of see it?
Yeah. So you're saying A plus B, reverse that is just B plus A to get back to A.
Yeah.
Okay.
There's another way to think about it. Okay, so here's our vector B minus A. So using our law of cosines here, the magnitude of vector B minus A, here's our angle between these two, sorry. Here's our angle between these two feet. Because I told you it should be AB times the cosine of the angle between the two vectors. That's what we mean by the angle between the two vectors.
Could you also write just B minus A instead of having those two lines? Does it mean the same?
B minus A is this vector.
I'm saying without the
Here's
vector.
A, here's B, here's B
I'm
minus
saying
A.
just the magnitude B minus A is the same thing as what you have written. Just do B
No,
minus A.
because the length of this vector is not the length of this vector minus the length of this vector.
But what is that?
Right.
It's whatever its length comes out to. You'd have to figure it out.
Well, what do those two lines represent? That's
The magnitude, the
Yes.
length of it, whatever the length of that vector is.
So why can't you just do B, which is the magnitude anyway?
Well, I could call this the vector C if I wanted, and then call that C.
Well, I'm saying why can't you just call that B minus A?
Because the length of this is not the length of this minus the length of this. Look, imagine I draw a vector, and it's exactly 2 meters long.
Okay.
And I draw this vector, and it's exactly 2 meters long. Now let's look at this vector. This vector is not in length 2 minus 2, or 0.
Yeah.
So the length of this is not the length of B minus the length of A.
I know. see a but.
Huh?
I don't see a but. I'll take your word for it.
Look, how long is B here, roughly?
It's vector B.
Let's say that B here looks like it's what? About 12 inches?
Sure, 12.
Or about 12 inches. Okay. How long does this look like it is?
12.
Maybe a little bit longer, or shorter. Maybe it's 11 inches.
Okay.
So B is 12 inches, A is 11 inches.
Okay.
What is B minus A?
1.
1 inch. Does this look like it's 1 inch long?
No.
So the length of B minus A is not B minus A.
Are
B
you
minus A
saying-
is like 1 inch.
Are you
The
saying,
length of B minus A is like 11 inches. Or maybe it's a foot.
Are you saying the point is the vector B or the whole line?
This vector whoop, is B minus A. The vector A is this. The vector B is this. The vector B minus A is this vector.
Okay.
That long vector, well over 1 inch long.
Okay, but why are you writing it like that? With the magnitude dashes right there.
So they're finding the length of B minus A.
Because
Oh.
I'm going to use this theorem. This theorem says this length squared is equal to that length squared plus that length squared minus 2 of that and that times that angle.
Okay,
So-
I think I see it now.
Okay.
I see it.
So the length of this side squared is equal to the length of this side squared plus the length of this side squared plus 2 length of that cosine of our angle phi. With me? That's just using this formula with this triangle.
Okay.
Good? Now let's multiply this out. Now I just barely proved to you that this distributes the way you know and love. Now we didn't say what it means to subtract a vector, but it means exactly what you think it means.
It's just
When I have vector 2, 7, and I subtract vector 1, 6,
It's just one.
then that would be the vector 1, 1. So it means add the one that's scaled up by -1 if you want to think about it that way.
Yeah.
Okay, so now let's figure out what this is.
Okay.
The length of a vector, we already showed that the length of a vector squared is the same thing as that vector dotted with itself.
Yes.
Yeah.
So now I'm just going to mess with this piece and see what this piece is equal to. So this piece is the exact same thing as the vector B minus A dotted with itself.
Yes.
This is exactly the magnitude of the vector squared. The length of a vector squared is the same thing as that vector dotted with itself.
Okay.
The length of a vector squared is exactly the same thing as a vector dotted with itself. So I'm writing this out in a different way, and then we're going to substitute. So that is that. Now I just barely proved that dot product distributes.
Yeah.
So I can do this dotted to both those and this dotted to both those and add it up. So we're going to get vector B dotted with vector B. But what is vector B dotted with vector B?
B squared.
It's just B squared. A vector dotted with itself is the magnitude squared. Okay. And then we're going to get minus vector A dotted with vector B. We're going to get another minus vector A dotted with vector B, so minus 2 of those. And then we're going to get plus an A squared for the negative A dotted with negative A. You with me?
Yeah.
So B dotted with B right there, negative A dotted with B, and negative B dotted with A. Those two give me this. And then finally, negative A dotted with negative A gives me that.
We're getting
Huh?
there. Yeah.
Okay. I'm there.
Follow it?
Yeah.
So this is equal to this. So now I'm going to substitute this in down here. So now I've got, writing it in a different order, A squared plus B squared minus 2 vector A dotted with vector B is equal to, that was the left-hand side, is equal to the right-hand side. A squared plus B squared plus 2AB cosine of phi. And it shouldn't be plus, it should be minus. Minus. Good? I didn't lose you in that mistake? Okay, the A's cancel out on both sides. The B's cancel out on both sides. Divide both sides by -2. And I'm left with A dotted with B, vector, is equal to AB cosine of phi.
Oh my word.
There it is. So they're one and the same thing. Now, why do we want to think about it as AB cosine of phi?
Yeah, it's a good question.
That is because the way that we always think about this is take our two vectors. Sorry, try and draw somewhat straight. There's vector A. Here's vector B. A is up here, whatever it is. We'll pretend that A is equal to, I don't know. What does that look like it is roughly? 2, 3? Something like that. And we'll say that vector B here happens to be, we're going to keep it nice and simple. It's going to be something like 4, 0. You okay with that?
Yeah.
Yeah.
So what does it mean to take the dot product of it? What you are doing is you are essentially casting a shadow down onto this vector. And that gives you a vector like this.
But opposite.
And then you are scaling it up by the length of this vector.
What? You're shadowing what now?
So drop the shadow down from this vector. Imagine the sun was directly above it, casting down a shadow.
Oh, that's your right angle.
That gives me this vector right here at a perfect right angle. The sun's perfectly above heaven.
So
Think about that as like a shadow on this vector.
A broken vector. Okay, yeah, I get what you're saying.
And then we're scaling it up by the length of vector B.
Up. What does up mean? Scaling?
Scaling it, when I scale up a vector by 2, that means make it twice as long. When I scale up a vector by 4, that means make it 4 times as long.
Why they're called
When I
scalars.
scale a vector by 1/2, it scales it down to 1/2 its side, which is why we typically call it scalars. They're scaling the vector.
Is that why they call the word scalar?
Yes, that's why we call it scalar multiplication when you multiply by a real number. Because you're scaling it up or you're scaling it down.
That makes sense.
You're rescaling the vector. Now let's make sense of how all this is happening. What is the length of this vector? It's just A, right?
Or A.
If this is our angle phi right here, what is the length of this vector down here? It's just A cosine of phi. What is the length of like vector B?
Vector B.
It's just B.
Why is it?
It's a boundary.
Why is it not vector B?
Well,
Because we're looking at length.
so we're going to project the vector down right here, and that gives us this distance.
Which is that cosine.
So that's A cosine of theta, or phi. Now we're going to scale it up by the length of B. That's what this does.
But what is B?
B is just the length of vector B. So in our concrete case here, B would be 4 times A would be the square root of 2 squared plus 3 squared times cosine of whatever phi comes out to. We'd have to calculate it using 2 and 3. The arc tangent of 2 over 3, or 3 over 2. But geometrically, forget the numbers. Geometrically, what is this doing? That's why I want you to see geometrically what's going on.
Scaling.
When I say that A dotted with B is equal to AB cosine of phi, where phi is the angle between them, I want you, geometrically, what is that doing? It's casting a shadow down from A onto B and then scaling it up by the length of B. Or in other words, A cosine of phi is like the portion of A in the same direction as B. It's like its component in the B direction. So here's A's component in the B direction, and then scale it up by however big B is.
So you just add it.
So if B were 2, then that means scale it down to B and then double it if B's bigger than 1, or if B's 2 in length.
Okay.
So geometrically, that's what it does.
Okay.
That is the dot product. That's the easier of the two products.
Do we have time to do the vector product?
What time is it?
340.
3:42.
Yeah.
Let me introduce you to the cross product really quick. We won't be doing all these derivations that we did for the dot product for the cross product.
We'll assume.
Are they the same thing, different tool?
No.
They're very different.
Very.
So there's our dot product. Now let's define our cross product.
Read the textbook.
Yeah.
When we do vector A cross product with vector B, first off, you can only do this in 3 dimensions. Makes 0 sense to do this in 2 dimensions.
Yeah, right. Unless you have a one-dimensional vector. Does that make sense?
For the sake of this course, makes 0 sense to do this in anything but 3 dimensions. We're not going to worry about any special cases. Now this gives you a vector, C, where we know 2 things about C. The magnitude of C is going to be equal to A times B times the sine of the angle between them. Dot product gives you a number. A cross B gives you a vector. Cross product gives you a new vector. The magnitude of the vector is AB sine of phi. And what direction does it point in? It always points perpendicular to A and B. Let me make sense of this. Here's our vector A, actually here in the chalkboard. Here's our vector B, also in the chalkboard. Vector C, then, is a vector that is perpendicular to both those, so it's shooting out of the chalkboard at you, or it's shooting into the chalkboard. One of the two. We'll tell you how to figure out which of those two. So it's either pointing this way or this way. It has to be perpendicular to both of them. And its length is calculated this way. Its length is the length of A times the length of B times the sine of the angle between them.
Okay, I get that.
Now, how do you figure out which way it points? When you're looking at A cross B, you are going to use what we call the right-hand rule. You take your right hand, not your left hand. You point your pointer finger in the direction of the first vector. In our case, it's A. You point your birdie in the direction of the other vector, in this case B. Whichever way your thumb is pointing is the direction of C. So in this case, it's going into the whiteboard. Notice A cross B, vector A cross B, is not the same thing as vector B cross A.
Here.
So dot product happened to be commutative, cross product is not commutative. Because let's look at B cross A. B cross A, what do? Point my pointer finger in the direction of B, point my birdie in the direction of A, and whichever way my thumb points is the way the cross product points. In that case, it points out of the board. This one points into the board, this one points out of the board. So when you swap the order, they're equal in magnitude but opposite in direction. So A cross B is a negative of B cross A. They're the same vector but pointing in opposite directions. That is the cross product. Now calculating the cross product by trying to figure out the angle between them is sometimes a pain. If I've got a vector pointing this way in space and a vector pointing this way in space, it's really hard to find the angle between those two vectors. And so there's a way to calculate this by hand using determinants. Have any of you come across a determinant before?
Not even close.
Not even close. Never took college algebra course. So, determinants in 2 dimensions, if I have some numbers, A1, B1, A2, B2, in a little matrix like this. The determinant is A1 times B2 minus B1 times A2. It's A1 times B2 minus B1 times A2. Concrete case. 1, 2, 3, 4. Calculate the determinant. It's 4 minus 6. Or in other words, negative 2. That's called a determinant in 2 dimensions. Pretty easy. Determinant with a 3 by 3 matrix, not so easy. So when you want to calculate the cross product, you use a determinant in a 3 by 3 matrix. You make your first row your unit vectors, I hat, j hat, k hat. Your next 2 rows are going to be the components of your vectors. Your vectors have to be 3-dimensional vectors.
A subset X.
So it's going to be a sub x if you want, a sub y, a sub z, and then b sub x, b sub y, b sub z. And now, how do you calculate a determinant on this thing? To calculate a determinant on a 3 by 3 matrix, you take the number in your first row column, first row, first column, which in our case is I hat, and then you multiply it by the determinant of what isn't in your same row or column. So you multiply it by the determinant of right here, what's not in your same row and not in your same column. So in this case, it's AY, AZ, BY, BZ. So that was for I. And then you alternate adding and subtracting. So this one was positive. Next we do minus j hat times the determinant, ignoring its row and its column. So AX, AZ, BX, BZ. And then finally add on k hat times AX, AY, BX, BY. And that is how you will calculate the cross product most of the time. So let's just come up with a quick example and then we'll call it there. So we'll make up some vectors. Give me our vector A. 2, 4, needs to be 3 dimensions. 3. And give me some other vector B.
1, 4, 5.
Let's make one of them negative. Negative 1, 4, 5. So that there's somewhat of an angle between them. So we don't accidentally get something really close together. Okay, and so let's calculate their cross product using this. So we're going to do I hat, j hat, k hat. We're going to do
2, 4, 3, negative 1, 4, 5.
calculate its determinant. So what is this going to be? Rather than writing I hat, I'm just going to write the vector written out where this number is going to be the first component, second component, third component.
What?
So A.
Never mind. Okay, so we're going to do I hat
Okay.
times the determinant here.
So
What's 4 times 5 minus 3 times 4?
Whoa, why are you
8.
doing that?
I just calculated this determinant. I'm not going to write out all these numbers on the calculator. It looks like a ton of algebra, but you can do this in your head pretty quick. So it's this times this determinant. What's the determinant here?
You cross and then
4 times 5
Oh, 20.
minus 3 times 4.
12.
What's 20 minus 12? 8. Now subtract j hat. What's 2 times 5
10.
minus negative 3? 13 minus negative 3. Minus negative 3. So times 13. And then finally, what's 2 times 4
8.
minus negative 4?
3.
12.
8 minus negative 4 is 12.
Oh, so, yeah, okay. I got you.
Plus 12 k hat. So in other words, the dot product gives us the vector, and our vector is a new vector, 8 minus 13, 12. There's the vector perpendicular to both these vectors. If I were to ask you to find the vector perpendicular to both those vectors, that would take you hours. Trying to think about all of it. There it is, it's that simple.
Okay.
So this looks like, holy cow, but in practice, it's not bad at all.
Why do you mean it would take hours? How is that?
If I just asked you to do that without giving you any prompt. Prior to today, I said, here's a vector pointing like this, here's a vector pointing like that. Find the one perfectly perpendicular to it.
Just do that.
Well, now you know.
Seriously.
Okay.
Talk about it.
I'm saying, appreciate how amazing it is that we can do something like that so simply.
Yes.
Thank all of those who further field.
Okay, and I won't be proving that that's the case, that any of that is that way. The cross product is hard to get geometric interpretation for, especially when you're not comfortable with
Oh,
determinants.
that's just a matrix. What is a matrix, by the way? Like, what are you drawing there?
A matrix, so the same way that a list, you know, a list is an ordered collection of numbers.
Yeah.
You think about a matrix as a list of lists.
Okay.
Here's the first list, here's the second list, here's the third list.
Fine.
That's good to know.
It's just a two-dimensional collection of numbers. If you've done some programming, you've created matrices by like putting an array in an array
Oh.
of arrays, create a matrix. Okay. Same thing. Okay, that's it. I'm barely able to fit this. This is going to be a big class. It's going to be lots of lecture. If you were hoping for breaks, you're not going to get them. That's how this is going to have to go.
This is better than calculus.
Any questions? I know that's a lot to take in, and we didn't do the last couple example problems. If you can't follow the thinking in them, feel free to text me or whatever, and I'll try and help you think it through. Or look at videos of it. I don't know. Whatever helps. You'll
Is
find
this
it.
the same textbook you used
Yep.
a couple years back?
So you can watch those lectures where I probably had more time to delve into it.
3 hours.
Okay. Any other questions? All right. See you guys next week.
That one for this week.